apologize for the quality of my voice as well. I've got come down with a cold today, so I hope it holds out for a few minutes. Okay, so I'm going to talk about SubDL. This is paraconsistent logic, a new generation paraconsistent logic, very interesting properties, a little different from the way things have been done in the past. I think it's an important line in logic. So I'm going to kill it and then resurrect it. You'll see as we go along. Very pleased to be able to do this here today in this conference. So there's a plan. We'll try and stick fairly well to it. I'll introduce the logic. A little bit complicated, but we should be able to go through it quite okay. And this is logic due to, as far as I know, due to a couple of people who are around here. So I hope I get it right. Yeah, well, it's got various components, which I'll talk about along the way. I'll say something about what it's intended to be for, and then I'll argue that there are things wrong with it, and try to suggest a simple fix that gives it at least a chance of going forward with its intended use. And then in the final part of the talk, if there's still anybody around and we get that far, I'll try to make sense of the system a little bit on the semantic side, at least, making some steps towards getting some algebraic semantics going for this kind of system or for systems in this vicinity, and mention some of the challenges ahead for that. So, okay, let's jump straight in. Here's SubDL. SubDL is a substructural logic that has various parts. It has an implication negation part that's very reminiscent of weak relevant logics. So this is exactly the implication negation fragment of the logic DW. And importantly, there's a conjunction operator, which is intended to be just ordinary AND. I mean, it's not the case in contrast to some substructural logics. There aren't different kinds of conjunction, different kinds of conjunction. There's just the one AND and the one OR, and here's the AND. And it has the sort of properties you'd expect it to have. Conjunctions imply they're conjunct, it's commutative, it's associative. And we have this axiom that's sometimes called the conjunctive syllogism, which is a special feature of the logic down at this level. Disjunction is just can be introduced simply as the De Morgan dual of and we get all the De Morgan laws, usual duality, and distribution of and over or, and excluded middle in that form. So this is the basic, the sort of internal part of SubDL. It's very close to the weak relevant logic DK that, to the best of my knowledge, was introduced by Routley and Meyer in the days before Richard Sylvan changed his name, back in about 1976 or so. So that's all old hat. It's all kind of well known. Well, not quite, but we'll see. What makes the logic really interesting is the addition of another implication connective. This was written as a double arrow. And we have a couple of axioms there saying that the single arrow is stronger than the double one. And then on this double arrow level comes the surprise that what we thought was ordinary conjunction is actually the operation with respect to which we get this residuation postulate. So it's a multiplicative conjunction in the usual way that think about this in substructural logics. Disjunction, though, is the additive notion. It's ordinary extensional, truth functional sort of conjunction, at least on the double arrow level of the system. So this is kind of bizarre when you come across it, that the multiplicative conjunction and the additive disjunction are each other's De Morgan duals back on the inner level of the logic. But it is so, and it kind of works. The rules of inference are straightforward. There's detachment for, of course, that holds for both of the arrows, and replacement of equivalence, which only holds for the single arrow. So recapping, it's a substructural logic, or 2 for the price of 1. There's the ontology of propositions on the fine-grained level is something like the weak relevant logic DK. It's not exactly DK because the disjunction isn't exactly DK disjunction, and the conjunction isn't exactly conjunction as set forth by Meyer and Routley. But anyway, it's that kind of logic. And there we are, these are associative commutative operations. They're dual to each other. And we have the problem of trying to sort out what they really are. But along comes at the higher level or more abstract level part of the logic with, of course, a different sort of ontology of propositions. And that satisfies the postulates of the very strong substructural logic BCK, or some affine logic we can think of as the appropriate fragment of linear logic plus weakening. And on that level, the AND turns out to be fusion, or what the linear logicians call a tensor product, but OR is ordinary additive disjunction. And it's worth noting that negation and the single arrow are not operations on the BCK level propositions at all. A and B might express the same proposition, but their negations, not A and not B, don't have to express the same proposition. This is not preserved. So it's kind of a little bit complicated, but interesting. What is it intended for? It's intended as a basis for paraconsistent mathematics, including mathematics of inconsistent theories. And that includes strong theories, mathematical theories that should be very classical, very usable in very classical ways. Essentially, the idea is that anything that classical maths can do, we can do better, except for maybe some bizarre stuff that only classical mathematicians would ever want to do. So we need a strong logic. So when we're doing mathematics with a logic like this, we think on the BCK level. We think of propositions as those given by equivalence in the strong logic, the higher level part of the logic. The kind of mathematics we want to do, and Zach is the person who's been doing this, by the way, not me, also includes seriously inconsistent theories, including naive theories, naive set theory in particular, for which you need a weak logic. BCK as presented normally in the literature on such things won't do. You need a logic like DK, or maybe a logic that doesn't satisfy replacement of equivalence or something like this. So SubDL is a logic, and it's quantified extension SubDL-Q, which I'm not talking about today. That attempts to be both. It attempts to be both strong and weak, strong where it needs to be strong and weak where it needs to be weak, and to run the two together in the right kind of way, which is fascinating, and it's as I said before, it makes it a very interesting departure in paraconsistent logic. Does it work? Spoiler, no. But with a little adjustment, and it's not a very big adjustment, maybe, to be seen. Now, just before I get to that meat of the talk there, I want to say a little bit about contraction. This is probably familiar to everybody who's left at this stage of the conference, but we'll push on with it. It's a structural rule that looks something like this. Whatever you can get from two assumptions of the same thing, you can get from just one, or you can think of it as the structural logical principle, the way to put proofs together, that says you can recycle used assumptions at no cost. And then when you come to discharge them with a deduction theorem or whatever, you can pretend you only assume things once. That's fundamental to classical logical worldview, of course, and it also holds in a lot of other logics, but not in BCK and not in DK. It's well known to collapse theories like naive set theory and similar things via Curry paradoxes. I'm not going to talk about those. You've probably seen those many times. And it's a prime suspect in a lot of other paradoxes, like the Sorites paradox. If you take an assumption like small change in color can't make the difference between something that looks red and something that doesn't look red, then one assumption of that doesn't look too bad. But if you make many assumptions, you can step through a long argument from something that resembles fresh blood to something that resembles a lemon, and putting them all together and pretending you only made the assumption once is exactly what's dodgy about that argument. And it's deeply involved in deep theorems that are not perhaps paradoxical, diagonal arguments, and this kind of thing. There's a nice quote here from Bob Meyer about contraction. He thinks of it as a sort of logical sleight of hand. I mean, it's what you do when you're sort of, slipping in the dodgy move and hoping people won't notice. He says that this leads people to confuse sleazy tricks with interesting theorems. And whenever the sleight of hand gets thickest, the move that pulls the bunny out of the hat is always contraction. And that's a nice quote from Bob. And of course, SubDL is set up to avoid contraction. It's absolutely central to the intended application of this kind of logic, that contraction should not be there. Unfortunately, as an instance of the distribution axiom, distribution of and over or, we have what you see. That's just where everything's negated. And of course, by De Morgan, we can pull the negation outside, and all the everything turns into its dual. And by contraposition, which is okay on the DK level, we get the distribution of or over and. That's not too surprising, but carrying on, since either of the two, A or B and C, entails this conclusion, in particular A entails A or B and A or C, and as a special case of that, A entails A or A and A or A, but hang on a minute, at the BCK level, A or A was just supposed to be the same thing as A because the disjunction here is additive disjunction. This is provable. And so two of them implies two of the A's. And in consequence of that, we have that A implies A and A on the BCK level. And that's contraction, because remember that the and at this level is fusion, not the kind of conjunction that we all know and love from logic 101. So that's bad news. It means SubDL, as presented in the literature, is not fit for purpose. You get contraction in it. However, we can fix it, I think. The bad guy in it seems to me, the axiom that's got blood all over its hands is this distribution principle. Well, we could also pin the blame on the De Morgan laws or something like that, but hanging on to the general idea of doing logic in this form, the axiom that has to go is this distribution of and over or. So what we can do with this is simply rewrite the single arrows here as double arrows, and hang on to it at the upper level. So we can use distribution of and over or on the BCK level when we're doing mathematics, when we want strong theories. We want to make classical sorts of moves. We can do that, but it isn't supported by an identity between the propositions down at the fine-grained level. That's my suggested fix, and that's a minor adjustment to the logic, very minor. Typographically, it's very small adjustment, but it has major effects. The distribution of or over and is no longer derivable because that essentially depended on having a single arrow there. And the logic becomes contraction-free. We can prove that, very, very, very easy to prove that. Here's a little model. There's nothing deep about this model. It's just a little four-valued thing, little algebra that happens to satisfy the postulates. And if we look at and or there, then given that that the underlying structure of propositions is a chain, 0 at the bottom, 3 at the top, and or look pretty much like what you'd expect and or to be, except that 1 and 1 is 0 instead of, so it's not, and is not idempotent. And of course, by De Morgan duality, 2 or 2 comes out as 3. Otherwise, these things just look like what you'd expect them to be. We can actually define a lot of different single arrows satisfying the decay postulates on this thing. I've just chosen one there that works, and it doesn't look too surprising. There's nothing bizarre about that. And double arrow, we get on the double arrow level, what's happened essentially is that the values 2 and 3, which are the designated values, of course, for the single arrow, they've got collapsed together. We just they're equivalent, and so the single arrows just has that table because that's what works, and so all the postulates are satisfied, including the new weaker version of distribution and over or, but distribution of or over and fails because of the fixed point of 1. Well, because of the case where A, B, and C are all the value 1, and contraction in the usual form that we think about it, just using the arrow, also fails. And it's worth noting that is a particularly convincing failure of contraction because the conclusion there, the B in the A implies B, the B is 0, it's the bottom guy. So, even in that case, contraction fails. So the logic is contraction free, and things can go ahead. Now, in the few minutes that I'm forcing you to stay behind here, I'd like to say a few things, at least make some steps towards getting semantic control of this logic. I don't have a nice semantic theory, but I can share some thoughts towards sorting out the algebra of this logic. A propositional model, just emphasize again, I'm not talking about quantifiers here, but I think pasting quantifiers in won't be too difficult. The propositional model has various components. There's a semi-ring for and or with De Morgan properties and ordering. I'll say something about these in a minute. There's also a definition of the single arrow of the DK bit of the logic, and that I think can be done in the traditional way that it's done in relevant logic. Then we need to impose this congruence of some sort to get the BCK level of propositions and some special postulates. I'll go through this in a moment. It would be nice to get beyond this and give some kind of semantics, like a generalization of the Rautli-Meyer frames or something like that, and to get some good proof theoretic control with a cut-free presentation of some kind, but I don't have anything to offer of that sort. So what are these De Morgan semi-rings? I noticed that some experts on semi-rings in the audience, so this is going to be very familiar to some people. So semi-ring is a set with a couple of binary operations. This is a commutative semi-ring, so they're both associative and commutative. They're usually referred to as multiplication and addition, and each of them has an identity. So both the star 1 reduct and the +0 reduct are commutative monoids. There's an extra postulate here that the 0 eats the semi-ring under multiplication. That the additive identity is a sort of black hole on the multiplicative side. That's not part of the definition of a semi-ring, but it's a postulate that a lot of important cases do satisfy, including this one. Then the De Morgan bit, which of course is going to model negation down the track. We have an operation that's a dual automorphism. It maps stars to it maps a multiplication to addition in the usual way. It dualizes everything, and it's a period 2. Of course, we get the dual of this postulate as well, that the bar of A plus B is A bar star B bar. That just follows, and lots of other nice properties. I want to go on to add order. So we want to model propositions with this. So there's going to be an order, which we take to be a partial order on D, and we take it that the dualizing operator reverses the order. So this is corresponding to contraposition. And we take AB to be ordered less than or equal to A. It will follow from duality that A is less than or equal to A plus B as well. That's a De Morgan semi-ring with order. But for the semi-ring, for it to be an ordered semi-ring, a stronger condition would also require that this sort of monotonicity fact that if A is less than or equal to B, then AC is less than or equal to BC. And again, the same thing holds for plus by duality. So we have this kind of an algebraic object. These things could be studied independently of SubDL, And so there's going to be some theory that we can leverage here. Of course, that's going to model conjunction and disjunction negation for us. A little example here. Do I have time? Yeah, just about. So you can see that this is a familiar structure. This is a 4-element Boolean algebra, essentially, which is, among other things, De Morgan semiring. But we can provide it with an order that's not the Boolean one, with a total order like this. Now it's a De Morgan semiring with order, but it's not ordered. Right? It's not an ordered De Morgan semiring. Not under that order. There's a different order, of course, under which it is. So this is the kind of, there's just a quick example. It's the sort of thing I'm talking about. Yeah, there's the failure of ordering. B is below A, but B star B is B, and A star B is 0. So it's not an ordered structure. Ackermann groupoids has been around for 50 years or so in the literature of non-classical logics. Just the basic structure for modeling, originally for modeling relevant logics and their rivals, but for substructural logics and similar things, we have a couple of operations corresponding to fusion and implication, and with obvious postulates. This element E is a left identity, and we have ordering and residuation. And if you want to throw in other connectives, or the positive cone is the stuff above the identity, and the model is what you expect it to be. These things at the basic, in the basic level correspond to B sub arrow, very weak. Logic, if you want other connectives, you make the order a lattice, a distributive lattice, De Morgan lattice, whatever you want. And generally to get stronger logics, like BCK or R or some other stronger DK or something, you add postulates governing the dot, and sometimes other connectives, but that's basically how you model these things algebraically. It's a very general class of structures. And so these things are the components. Getting towards SubDL, we want a structure that's both a De Morgan semiring, or an ordered De Morgan semiring with order, and we want and or to be the operations there. And at the same time, we want it to be an Ackermann groupoid to model the DK bit of the logic. We'll then want to impose some sort of relation partitioning the elements into a set of classes and define order on those sets in the pointwise way. We'll require the equivalence class of E to be the positive cone because at the BCK level, we want just one designated value at the top of the structure. And of course, everything above E is true. We'll want this to be a congruence in the usual way with respect to the De Morgan semiring, but not with respect to the Ackermann groupoid operations. We're going to require that the quotient algebra you get under this equivalence, under this congruence, is an ordered De Morgan semiring, and we also require that that when we raise the addition operation of the semiring to this level, it becomes idempotent. And lots of good stuff follows. Follows that, of course, we get a joint semilattice. And if the semilattice is complete, which of course it is in the finite case, but in the infinite case, we might have to complete it by usual tricks. Then we can define the arrow. It's just the join of the elements satisfying the residuation. And then In the finite case, we can even define the double arrow on the elements of the propositional structure itself, but that's I don't see how to raise that to the infinite case at the moment. And we need to add some more postulates to get dk rather than b or something. We'll need excluded middle and contraposition in the theorem form and so forth. So how close are we to having some structures that we can actually talk about as modeling SubDL? Not quite.
Just to let you know, we've probably got about 2 minutes left in the session.
Yep, yeah, I'm on the last slide or next to the last. We're not quite there. Working back from the double arrow on the quotient algebra to the double arrow on the propositional structure has to extend to the infinite case. I don't know how to do that. We're missing some theorems, the theorem forms of the relationship between the arrows and semilattice properties and crucially, of course, the distribution axiom. Though we could make that part of the definition of ordered, as is often done algebraically, or call it strongly ordered or something. But we're in the right ballpark. We're in the right family of logics. We have some structure where we have BCK somehow superimposed on a DK basis, and at least having these small models like the 4-element one that I showed you gives us a test bed for ideas. We can say, well, what if we put this in, or what if we restrict to that case, and so forth. It's good to be able to do that. So, as adjusted, SubDL lives. Yay! It rises and rides again. There's lots of future work. Got to close the gaps on the previous slide of the things I don't know how to do. It'd be nice to rework this as higher level semantics of some sort so that we at least get more informative completeness theorems. And it'd be nice to have a really coherent account of a class of logics in the style of SubDL, so that maybe we can see SubDL as a distinguished one of them or something like that. Of course, we've got to add the quantifiers. I don't think that's going to cause major snags, but of course, like a lot of things I don't think, it may not be as easy as, it may fail to be false. And finally, it's necessary to evaluate the effect of my little adjustment on the program in paraconsistent mathematics, and that one I cheerfully flicked to Zach. So there we go. That's it for now.